understand black holes quantum mechanically, you must have a boundary beyond which the black hole becomes an elementary particle, okay, or something else. Now, for example, what happens in classical physics? In classical physics, this size goes to 0, okay? Why? Because the Planck length goes to 0. So that's why in classical physics, first of all, in classical physics, the elementary particles are simply massless, okay? They are infinitely many and they are massless. So the Compton wavelength is always infinite, okay? And because h bar is sorry, Compton wavelength is, well, depends how you normalize, okay? Depends on the how you introduce the mass. But in any case, when you go into classical physics, the h bar goes to 0. And so the notion of the elementary particle simply gets abolished, okay? It can become infinitely, the energy can go to 0, and you get infinitely number of them, and so on, okay? So, in classical physics, the elementary particles and black holes, they never meet, okay? Because black holes can be arbitrarily small and finite mass. So, here's the thing, right? If we are classical, then h bar is 0, then I can have finite mass black holes, and they can be arbitrarily light, okay? Why? Because Planck scale is 0, and Planck mass is also 0. So therefore, I can make a black hole that is arbitrarily, this classical black hole, which is arbitrarily light and arbitrarily small. Now, in a semi-classical picture, h bar is non-zero. But remember, we defined it, semi-classical picture. In semi-classical picture, black holes are infinitely heavy. So the mass is infinite, Newton's constant is 0. So therefore, Planck length is again 0. And correspondingly, again, they don't meet. Because any finite, of course, now you can have elementary particles, they can have finite mass, but black holes are infinitely heavy, okay? So, in other words, in classical picture and in semi-classical picture, elementary particles and black holes, they never meet. They are two different worlds, okay? They only meet in quantum theory, in which everything is finite. Newton's constant is finite, black hole mass is finite, Planck constant is finite, and Planck length is also finite. Then there is inevitably there is a meeting point. And this is very nice, because this is one key how to understand that you can go, because you see, if the two entities never meet, then it's extremely hard to conclude that black holes should have some quantum substructure, right? Because they never meet. You can always say that black holes belong to they are out of this world, okay? I can never produce them because they are either infinitely heavy or I don't have an elementary particle, so they never meet. And so they are totally mysterious. But the fact that they meet tells you that demystifies the problem, because it tells you that black holes are normal guys. You should be able to produce them by putting together elementary particles. Moreover, you should be able to produce them in particle collisions, okay? And after all, they are not that mysterious. Of course, they are beautiful, but not that mysterious, okay? And this is the point. This is very important, okay? Okay, so now let's go to the next step, okay? Let's go to the, we mentioned this briefly also, Rami described this. Let me just remind you in very simple terms, okay? Now, in semi-classical case, right? In semi-classical case, when we have, okay, what I wrote there, okay, semi-classical. Okay, we have infinitely massive black hole. Newton's constant goes to 0. The gravitation radius is fixed. And h bar is non-zero. Okay, so in this limit, as you know from the previous lectures, Hawking did computation which shows that in this limit you have black holes, you have a radiation coming out of a black hole, okay? And the spectrum of radiation is exactly thermal. So the picture is that you are getting a spectrum of radiation which it has characteristic temperature, so-called Hawking temperature, which is something like h bar over r. Let me I'm also setting Boltzmann equal to 1 and etc. This is the characteristic temperature, and correspondingly, the black hole radiates. Now, because black hole radiates, you have a Stefan-Boltzmann law of radiation, okay, as if it radiates like an ideally black body. So there is a time evolution of energy release the energy, right? So we have something like okay, something like that. Now, okay, we have this Stefan Boltzmann law of energy release, okay, by a black hole. Now, this may create a false impression that the black hole is losing its mass. But actually, it's not losing its mass because mass is infinite. Okay, so therefore, despite the fact that it's like an infinite capacitor in that limit. Okay, despite the fact that it radiates, okay, it will never decay finally. Okay, it's eternal. Now, from here you can evaluate the lifetime of a black hole. Okay, to evaluate lifetime of a black hole, you can. It's very easy because